So the title of Margie's talk today is Shallow Water Management Models for Chesapeake Bay, and we're actually going to get under the hood in this talk on some of these models. Margie.
Thank you, Raleigh. So I think this actually follows pretty nicely from Rich's last talk. He gave an excellent summary of these models that have been used over the past several decades. And here, this talk is really kind of looking forward now. Where can we go in the future? What was the next generation of the models going to look like in the Bay? And to do that, we really do, as Raleigh said, need to look under the hood and look maybe some places where things can be improved. So, first of all, I want to acknowledge my collaborators here, Aaron Beaver from Anchor QEA and also Raleigh from UMCES, and really appreciate all their input and the many years of discussions that we've had about shallow water modeling. So, shallow water means, of course, different things to different people. I started out my marine science career studying the open ocean. So to me, back then, the continental shelf was shallow. I think a lot of people here go out and think, it's shallow if I can go wade into the bay and my shorts don't get wet. So here, the definition I'm going to use is 3 meters. So waters that are shallower than 3 meters, I'm going to be considered to be shallow. So here on the right, you can see this is a map of the bathymetry of the bay, and the red here areas are the surface area regions where the bay is less than 3 meters deep. So you can see there's really quite a large fraction of the surface area of the bay is considered shallow by this definition. So these waters are, the shallow waters of the bay are important not only because they make up such a large fraction of the bay, but for a number of other reasons as well. First of all, these are really the waters that we see. Those of us who live near the bay and the part of the watershed close to the bay, we see the shallow waters. This is near where we live. This is near where we work. This is where we go spend some weekends looking at on or in the shallow waters of the bay. Unfortunately, this is historically also where we've seen significant degradation of the bay waters. This is where some of the worst algal blooms can be. This is where some of the muckiest water is. On the bright side, however, these shallow waters are also where we're probably most likely to see early responses to management actions. Improving or eliminating hypoxia in the deep main stem of the bay is going to take years and years if we can ever do that. But where we really are already seeing dramatic improvements in the shallow waters, with 2018 being a third consecutive record year for underwater bay grass growth, for example. So for a number of these reasons, a lot of the researchers and managers are really focusing in on shallow waters. So why do we need improved models of these shallow waters? If we can go out and observe them, if we can measure them, why do we need the models? Well, this is all about what Rich just talked about. Really, the managers depend on these models to really assess the impacts of various different alternative management strategies. And in addition, we're looking now at climate change in the future. We need the models in order to look forward to see how, if the management strategies that we developed that we thought were going to work when we developed them a decade ago, are they really going to work well enough to improve the health of the bay in 2025 or even 2050? So the models are really important. So unfortunately, these shallow waters are also probably the most challenging to model. I think this image here of the Chester River is really really shows this pretty clearly. You can see these complex linkages between the land and the meandering waterway here. You can see the forests leading in, the farm fields, the houses and structures, and then the bay in the background. So in these coastal very shallow water areas, processes vary on very small time and space scales. So we're going to require really super high resolution estuarine models to simulate these processes. On the other hand, we also, in these systems, they respond very strongly to the distant forcing as well. So the systems are responding to what's going on as the Chester River, for instance, shown here, meets the Chesapeake Bay. So we need models that are simulating not only these very high resolution processes, but also on small time and space scales, but also the larger time and space scales as well. And so there are, over the past 5 or 10 years, there have been a considerable effort on numerical modeling methods and new technologies to develop models that resolve both these very high frequency small space scales as well as the larger space scales. And these models are being currently run in the Chesapeake Bay. They're also being run globally in estuaries around the world, but they're not yet part of the Chesapeake Bay modeling system. So realizing this back in 2012, so this is quite a while ago now, we began some of this work. STAC, the Scientific and Technical Advisory Committee for the Bay program, recommended to the management board that a prototype multiple modeling effort be implemented involving both the skill assessment of multiple models and the peer review of these models in order to identify those that best match or best reproduce the available data in the shallow waters of the Bay and its tributaries. Only a short time later, in February 2012, the management board pretty enthusiastically responded and said, yes, a demonstration project in a well-monitored system would serve as a prototype for the application and assessment of multiple models, and said that the EPA was now examining the potential to fund a few prototype shallow water models this year. So we were really heartened that the management board really seemed to understand the value of using multiple models in a research program such as this, and using the multiple models to increase scientific and management and stakeholder confidence in the tools that were being used to support and inform management decision making. So fast forward a year later, and this RFP was released to fund this multiple modeling effort in the shallow waters. So this effort funded 5 different modeling teams. We have a model comparison team, myself, Aaron Beaver, and Raleigh Hood. And then we have 4 separate modeling teams. From Old Dominion University, we have Dick Zimmerman, John Klink, and Victoria Hill. And they were primarily focused on using the Grasslight SAV model. We have the Schism team from VIMS, Joseph Zhang, Harry Wang, Fei Yi, and Jingyu Wang. Then we have the ROMS team, Jeremy Testa, Damian Brady, and Kelly Cole. And finally, we have the Bay Program investigators Richard Tian and Ping Wang representing FVCOM, and then the regulatory model, the water quality sediment transport model. And I also want to mention that we had this advisory team, Lou Linker, Carl Serco, Larry Sanford, and Kevin Sellner that have been involved in this project from the very beginning. And I just wanted to mention before I forget that a number of these folks are presenting some of the work that started as part of this project here today. So a number of these people are here today, but in particular, Joseph Fei, Zhengli, and Lu all have presentations in this session tomorrow afternoon, Change in the Chesapeake, Moving Toward Finer Scales in Watershed and Estuarine Modeling. So if you want to hear more about shallow water modeling, I highly recommend you go see those presentations. So the overarching research questions of this project is really digging into the estuarine model, which we call WQSTM. I'm going to use that a lot. I can't say it very well, but that's the Water Quality Sediment Transport Model. It's also the regulatory model for the Bay program. So we really want to dive into this model and look to see, is this adequate for modeling the shallows? Now, keep in mind, it wasn't developed really to model the shallows, so you can probably guess what the answer is going to be. But we're looking at that, and we're going to look at how much better the higher resolution models that actually employ these new modeling technologies, how much better they are able to represent the data we now have in the shallow waters. We're going to look at whether these high resolution models have similar skill to each other, and also how they react to changes in inputs from the bay, and also changes in inputs from the watersheds, and how they're responding to the nutrient reduction strategies. So just a brief outline of my talk today. I'm going to first talk a little bit about the study site we're using. We're working in the Chester River. I'm going to talk about the 4 participating models, their similarities, which includes all the forcing that was used for the models is all identical. Also the differences between the models, their grids differed considerably. And then I'm going to talk about the hydrodynamics first, basically with the idea that if we can't adequately model a conservative tracer such as salinity, do we really have the ability to model a much more complex system that ecological variables such as chlorophyll and oxygen and TSS. So I'm going to first talk about the hydrodynamics and then go on and talk about some of the ecological variables, in both cases looking at model performance and some sensitivity experiments, and then I'll end with a summary and perhaps some recommendations for looking forward into the future for the next generation bay models. So our study site is the Chester River. This is a very small, or relatively small, tributary in the northeastern portion of the bay. Zoomed in here, you can see the Chester River is about 65 kilometers long, curved around here. This is at the boundary of the Chester River. The depth is about 10 meters, and there's a narrow channel throughout that extends about 45 kilometers down the bay. It's about 18 meters deep in its deepest portion over here, and gets shallower to about 8 meters deep at upstream. So why did we choose the Chester River? Well, the simple answer is that we have a lot of data in this location, and this is summarized here. First of all, we have two water quality monitoring stations shown by the red stars. Up here is ET 4.1 and down here is ET 4.2. So for those of you that might not be familiar with water quality monitoring data in the bay, we have the cruises sample these stations once a month in the cooler months, twice a month in the warmer months, and we've got these time series going back since about 1985 or so. So we also have 3 sites with the pluses here, 1, 2, 3. We have continuous monitoring sites. So here we are getting, in at least the warmer months of the year, daily or even higher frequency monitoring information on water quality and physical variables. And then finally we have data flow information as well, and shown on here in these red dots. So these are basically bi-weekly data that we get from, and also in the warmer months, from those sources. So the time period we're going to look at is 2003 to 2006. This is when we had probably the most amount of data from this site. And the variables, we're going to look at 5 different variables today: salinity, temperature, dissolved oxygen, DO, chlorophyll, and total suspended solids. So this is just, this wealth of data is just fantastic in order to use to evaluate our models of this system. So we've got 4 participating estuarine models. Listed here, and I'm going to try to be consistent with the color coding here. So the WQSTM, again, this is the regulatory bay program model. And we've got 3 higher resolution models: FVCOM in red, Schism in green, and ROMS in purple. So again, the bay program model is a low horizontal resolution model. It has a structured grid and a Z-grid, which means that basically the depths of each vertical layer are the same. So are always about 5 feet or so. So again, this model was developed to look at the bay as a whole, really more the main stem bay than the shallows. So as a little spoiler alert, it may have some issues in these shallow waters here. But again, that's not what it was designed to do. The 3 high-resolution models are FVCOM, Schism, and ROMS. FVCOM is one of the unique attributes of this model is that it has a triangular grid, so it's able to really resolve the coastline quite well by using triangles rather than rectangles or squares. It also has a sigma grid, which means that even in the shallowest areas upstream, where the water, again, is very, very shallow, we still has a full 10 different vertical layers, whereas a Z-grid means that you've got fewer vertical layers as you get into shallower water. We also have Schism, has a couple of unique features. It has a hybrid horizontal grid, so it has the triangles along the coastline, so it can really simulate the coastline very well, but it's also got rectangles in the channel, so it also has a high resolution in the channel too. And it uses a unique hybrid vertical scheme, kind of combining the best features of the sigma and the Z-grid. Then we have ROMS, and probably this could be thought of as having the highest resolution of all the models. It has a structured grid, so it's got the same resolution pretty much throughout the entire Chester River. So in some portions of the river, it's got very high resolution, where the other models does not. We also have, these models are linked to Biogeochemical Water Quality Model, ICM. So all three of these top three models are linked to ICM, but the implementations are a little different. So we're going to see some different results here. The first two are offline coupled, and then the third schism here is two-way coupled, so that the biology is affecting the physics and the physics is affecting the biology. And another interesting thing is that the schism model actually does not have an inorganic sediment model. So we're going to be looking at total suspended solids, but the schism model uses basically an empirical parameterization for sediments. So another thing to keep in mind. So just so that you can get a kind of a visual feeling for the relative grids of these various shallow water models, I have the four shown here. So if you just simply look at the number of grid cells in the models, you can see you've got about 200. In the regulatory model, we've got about an order of magnitude more in schism and FVCOM, maybe a factor of 2 more here in ROMS. If you zoom into this upper Chester here, where we're going to be looking at some of the results, you can see that here the water quality sediment transport model really has only one grid cell in this 4 kilometer by 3 kilometer square. We've got many more dots here in FVCOM, even more in schism and ROMS. In addition to looking at just comparing the total number of grid cells, it's really important to look at how the grid cells are distributed, where the higher resolution is in these grids. So, and this differs quite a bit. So in FVCOM, we have very high resolution along the coastline. This is very clearly well resolved here. In schism, we actually have a higher resolution in this channel than we do along the coastline. So that these two models differ in that way. ROMS, again, is high resolution everywhere, and so it has particularly much higher resolution at the bay mouth than does either FVCOM or schism. So this actually has a lot of implications for the bathymetry. Now, each of these models were provided with the same digital elevation map, the same bathymetry, but each model had to interpolate the bathymetry onto their own grid. So as a result, each of the models are seeing somewhat different bathymetries. And so that's what I'm showing here. And I'm going to show a whole bunch of these figures. So I'm going to go through it here thoroughly once. So basically this figure here is showing a transect upstream. So this is the mouth of the Chester River, and then this is distance upstream from 0 kilometers to about 65 kilometers, and so this is the head of the Chester River. So basically, as you go up here, these various dots correspond to the distance along the Chester River up here, with this final dot being represented over here. So in each of the cases, we've got these 4 different models are going to, in each figure, are going to be represented by the 4 different colors, and then the black line in each case is going to represent the data, or best estimate of the system. So here, the black line represents the observed bathymetry. So first of all, what do we see? Well, the purple and the red lines actually track each other quite well. So FVCOM and ROMS are having very similar bathymetry. The water quality sediment transport model, the regulatory model, has very much shallower depths. Here it's pretty constant at about 4 meters, or here it's 6 meters throughout much of the Chester River. And it's really only schism that really can reproduce, for instance, the deeper channel here at about 38 kilometers, which is about over here. So in addition to having all the models use the same bathymetric information, we also provided the same model forcing to all the models. So the model forcing came from the Bay Program's estuarine model, so largely from the oceans, the bay side. So we have bay temperature and salinity from the estuarine model. So here in red, the bay temperature is shown, and down here we have bay salinity being shown. For just an example year over 2003, but we provided it for the full 2003 to 2006. Also, we've got the watershed inputs. All the models use the same watershed inputs so the same runoff. Here we have the freshwater runoff in blue, shown again for 2003. This is Hurricane Isabel, the big spike there. So all the models are using the same consistent forcing and then provided back to us daily output for these 4 years from 50 stations. And now we chose these stations carefully. 25 of these stations are where we have a lot of data, so that's where we can compare the relative skill of the models. And then 25 of the 25 stations, we actually don't have data. So it's really interesting to compare how well the models do where we have data. Turns out they often do very similarly, and compared to where we don't have data, where the models actually can diverge tremendously. So each of the modeling teams performed 3 different experiments. So first we had the realistic base case. So this is the results that we can compare to the observations to see how well the model is doing. Then we did have a series of hydrodynamic sensitivity experiments where we decreased the inputs from the watershed, the freshwater input. And then we also had an experiment where we changed the outer boundary condition where the Chester River mouth meets the bay. And then also we had the nutrient reduction scenarios. We received this information from the Bay program, so we have a 1985 scenario, a TMDL scenario, and an all-forest scenario. Okay, so I've introduced the project quite a bit, so finally some results. So I'm going to start again by talking about some hydrodynamics, so model performance in terms of temperature and salinity. So again, this is one of these transect figures for the Chester River mouth over here going upstream. And here I'm showing mean annual bottom temperature. So for the 4 different models in color and then the black line in the data. Again, along this transect here. So I think probably from the back of the room, you can probably see, all you can probably see is that a jumble of lines here together, and that's really the point here. All the models do very well in terms of representing the temperature. Also, they do, here I'm just showing 2003 temperature, but at the bottom, but they also do equally well at the surface, they do equally well at other years, they do equally well at other seasons. So generally, the models do well in terms of temperature, even the low resolution current regulatory model. But of course, much more interesting is salinity. This is what the ecological variables really respond to, is the stratification, which again is driven by salinity. So this is a much more ecologically relevant variable to look at. And here we see some different results. So again, this is the plot like I showed you for temperature. This is the mean annual bottom salinity this time though. Again, from the mouth of the Chester River upstream. So the first thing you can see is this line here, up here, where the regulatory model basically has the same salinity throughout much of the Chester River, about 6 to 8 parts per thousand, all the way upstream. This is in direct contrast to all the other models, which show this dramatic salinity gradient, which agree with the data shown here in black. So all the high resolution, although the regulatory model misses the salinity gradient, the other high resolution models all do similarly well. FVCOM is a little high, RONS is a little low, but generally they do very well. And just to show that this is not a unique feature of 2003, on the right here I have results for 2005 as well. And again, we see very similar results. With the high resolution models really being able to simulate this salinity gradient quite well. So in terms of stratification, which actually is the variable that we're most interested in, because probably this has the most impact on hypoxia and oxygen concentrations in the water. Here we have salinity stratification. So basically, by this I just mean the difference between the top and bottom salinity at these locations. So again, the data is shown in black. That's this point here, and then the 4 models are in the colors. So here you can see that the regulatory model here is really overestimating by almost a factor of 2 the stratification in the lower Chester, and also overestimating stratification here. And this is probably because we really have at such a shallow reach in the upper Chester, probably we may only have 2 vertical depth levels here in the water quality model. So it has a very hard time reproducing the stratification well. So this is actually overestimating the stratification, whereas the data in the high resolution models get this almost 0 stratification at this upper level in the upper Chester. So these are points where we have data. And one of the things I think I forgot to mention earlier is that a lot of these data points from the data flow here shown on these red dots are actually on the shoals of the channel, of shoals of the Chester, not in the channel of the Chester. So we're also actually interested in how well the models, how the models compare in the channel. Even though we don't have data there, we still want to know how the models compare. Are they reacting similarly or not? And it turns out that they actually look quite different. So the two high-resolution models are pretty similar in red and green here, these two high-resolution models. The regulatory model is really overestimating stratification through a large fraction all the way up to about here, throughout this part. Then it gets the stratification right kind of in the middle, and then back up at the very upper Chester again, it's overestimating stratification. So the high-resolution models are doing, however, pretty similarly, except for ROMS here, which has got a little issue with the boundary. So I want to just digress for a short time period before going on and talking about the hydrodynamic sensitivity experiments. And this is to look at a comparison. So it turns out that the Bay program actually has two estimates of salinity that were provided to us. One is from the hydrodynamic model that they use, which is called CH3D. And then we have another estimate of salinity, which comes from the water quality sediment transport model. This is essentially what's used for management decisions or involved in management decisions. And CH3D has been tuned quite a bit. And that information is then fed into the water quality sediment transport model. But the water quality sediment transport model actually has its own transport advection schemes, its own time step, so the salinity ends up being quite different between these two models, which is something we didn't realize going into this project. So it turns out that this isn't really an issue in the lower Chester or in most of the parts of the main stem of the bay. They're very similar. But it turns out in the very shallow waters, you can get a really big difference in salinity. And so this is what is forcing our ecology, our biogeochemistry, not this salinity here. So it's something that really to keep in mind and can be an issue for models when they're running ecological applications offline from the hydrodynamics. So that was just a little digression. And so now I want to go back into talking about the sensitivity impacts due to changing the watershed and bay inputs. So we did two different sensitivity experiments. In the first one, we reduced the freshwater inputs from the watershed by 10%. Those are the results I'm showing here. So on this figure here, I actually have 6 lines. This is showing 2003 salinity, mean summer bottom salinity. And the 3 dark lines represent the base case, and then the 3 light lines represent the 10% reduction. So now I'm sure in the back of the room, I can't even see much of a difference. So you can really only see 3 lines, and that's the point. They're basically reducing the freshwater input by 10% really has no significant impact on salinity or stratification in the Chester River. So the other experiment we did was to change the salinity at this boundary here, the boundary of the Chester River with where it meets the open bay. Here we changed originally, we used the CH3D boundary conditions that we received from the Bay program, but then we also switched to a low resolution schism implementation. So basically these two models, they performed pretty similarly. It's hard to tell which one is better, but there were some differences. So we applied, each model ran their simulations with both, and these are the results we get. So now we do see some differences. Here I'm just plotting the deltas, the delta salinity, the difference between changing this open boundary condition, the salinity here. So here we see a much greater impact than we saw with a change in the watershed input. And in fact, I think one of the most interesting things is that we see this impact all the way up here to the 55 kilometers. So changing the salinity that we use here actually impacts the estuarine salinity all the way up to here. So that was really surprising to us. Okay, so just to summarize quickly before I move on to the ecological, more ecologically relevant variables, we've seen that the high-resolution models simulate the shallow hydrodynamics quite well. Although all the models reproduce temperature well, we didn't need the high resolution for that. But really only the high-resolution models could get this upstream salinity gradient that we see in the Chester and many of the tributaries. And also one thing that I didn't have too much time to get into is that these models are very sensitive to the bathymetry. And that is coming up time and time again, but I didn't have time to go into that too much. Also, we found that the accurate information at the river mouth, where the river meets the bay, is absolutely critical. We found that a 10% reduction in watershed input really had no impact, especially compared to changing models, whereas changing the bay salinity has an impact all the way up throughout most of the Chester River. So this implies that we really have to have confidence in the bay simulation that we're using at the Chester River mouth. So finally, also just the other thing I mentioned is that running these biogeochemical water quality models offline from the hydrodynamics really can lead to some difference in skill, which needs to be considered and investigated further. So on to the ecological variables, we're looking at oxygen, chlorophyll, and total suspended solids. Of course, the reason we've spent so much time in the hydrodynamics is that these impact the ecologically relevant variables. But we're really interested here are these other water quality variables. So first of all, oxygen. So again, we've got another transect figure here. Oh, and now we don't have ROM's output for water quality. We just have these three models, the regulatory model, Schism, and FECOM. So here I'm plotting bottom oxygen up the river from 0 to 65 kilometers once again. And so basically what we see is we get the models all look very similar, including the high resolution model, except when you get up to the very upper Chester. And here, the high resolution models actually reproduce this increase in dissolved oxygen that we see as we get closer to the upper reaches of the Chester, whereas the low resolution models generally show decreasing oxygen as you get up farther. So again, these are compared to data. So this is where this is comparing the models at the shoals, kind of not in the main channel. So we also wanted to look to see how the models compare, even where we don't have data in the main channel, and that's what we're showing here. So here you can see actually the models diverge quite a bit more where we don't have data than they do where we do have data. In particular, we see that the regulatory model has very low salinity anoxia throughout much of the summer 2003 in both the lower Chester as well as in the upper Chester, which is quite different from the high resolution models, which show increasing oxygen as we go upstream. So we do have some data in the channel. We have these water quality monitoring stations, and so that's the information I'm showing here. We have ET 4.1 way up here in the upper Chester, and that's the top plot, and then we have ET 4.2 in the lower Chester, and that's what I'm showing here. So here again, you can see, just as we saw in the earlier plot, we get very low oxygen in the regulatory model at the bottom oxygen in all 4 years, not just in any one summer. At the upper reaches here, and also in the lower reaches, the model does quite well in the summer, getting the anoxia that is really observed there in the deep section here at ET 4.2. But the anoxia and hypoxia last longer, well into the fall, whereas the observations show the water's recovering from the hypoxia. The blue line here recovers quite a bit later in each of the 3 years. So I've talked a lot about oxygen. We also looked quite a bit at chlorophyll and TSS. Here on the left, I have an example of transect for chlorophyll, and on the right, a transect for total suspended solids. And generally here, I think that you can see that we get really quite a big difference between the models for both of these variables, both chlorophyll and TSS. Schism actually does quite well in both of these cases. And again, this is kind of interesting that it does quite well in terms of TSS without even having a TSS model. It just uses an empirical relationship for inorganic suspended solids. But, however, it does do very well in terms of reproducing the bathymetry and probably therefore getting the residence time correct in the tributary. So now for the last segment of the talk, we're going to look at how each of these models respond to the nutrient reduction strategies. For instance, we've seen that the chlorophyll and TSS are looking very different between these various different models, even the high resolution models. How do they compare when we apply these nutrient reduction strategies to the various models? So just a little bit about these experiments. In this case, we are altering nutrient inputs not only from the watershed, but also from the atmosphere, and then also from the open bay as well. And we're going to look at 3 different scenarios. Again, these were just obtained right from the Bay program. So we got lots of help from them. We have this 1985 scenario. So this basically is our reference point. These have relatively high nutrient inputs. Then we have the TMDL scenario, where we have lower nutrient inputs, obviously. And then we have an all forest. So we have VAR, which represents basically the case where all the watershed is turned into forest, and have very little nutrients coming off the land. And then finally, we have 2 additional experiments here. One I'm calling 1985 river only and 1985 bay only. And in these 2 experiments, basically we have the TMDL case, and we're switching the watershed back to what the condition in the 1985 in one case, and we're switching the open bay back to 1985 in the other case. So to look at basically the relative impacts of improving the watershed versus improving the open bay. So these are the results here. So now I'm showing the 3 different variables. We have bottom DO here on the left, chlorophyll in the middle, and TSS on the right. Again, we have on each of these panels, this is for summer 2003, we have 6 different lines. But again, you can probably only see 3 in the back. I kind of generally only see 3 up here. And so the point here is that we really get very small changes due to the TMDL. I should say that the darker lines are the 1985 lines and the TMDL are the lighter lines, but they pretty much overlay each other in many cases here. You see a little difference here, but generally the differences between the models, between the red and the green and the blue, are dramatically larger than the difference due to the TMDL nutrient reductions. And interestingly, we see a large concentration differences in chlorophyll and TSS between the models, even though they're all using the ICM model. So here, since it was so hard to see the differences, I've just plotted the deltas here. So again, here we have delta bottom DO on the left, delta surface chlorophyll in the middle, and delta bottom TSS on the right here, again for these 3 different models. So here you can see that the impact of the nutrient reductions is generally very similar between the models, especially between the red and green lines here. Very similar here in terms of DO, and relatively similar in terms of chlorophyll. So now, what if we look at the all forest scenario? So first of all, here I'm showing 1985 on the left. Now we're looking at just at bottom oxygen in each of the 3 cases. This is the 1985 scenario on the left, going upstream. Again, this DO increase as you go upstream in the high resolution models. Here's the TMDL scenario, which again looks pretty much exactly like the 1985 scenario. And then we've got this all forest scenario. So fortunately, if we turn all the watershed into forest, yes, we do see a change in the models. In particular, the regulatory model showed anoxia even under the TMDL here in the Chester River, but in the all forest you get the anoxia is relieved, but it's still a considerable portion of the river is under hypoxia. But we really see a dramatic improvement up in the upper Chester compared to the TMDL when you go from the TMDL to the all forest. So much higher improvements under the all forest, especially for the regulatory model. And the regulatory model is still hypoxic though under this all forest, whereas the other 2 models are not. So we are seeing differences between the low and high resolution models. So now we're going to do these last 2 experiments, last 2 sets of results where we're changing just the rivers or changing just the open boundary. So here I have bottom DO on the left, the change here, the change in surface chlorophyll and the change in TSS. And now for these sensitivity experiments, only the schism and FVCOM models were participated. So here you can see if we go back to the 1985 conditions in the rivers, as we would expect, DO decreases quite a bit, and TSS increases quite a bit. So just as we expect. And the interesting thing here is to look at how far downstream these effects were felt. So essentially they were felt about 25 or 30 kilometers downstream, but these changes didn't impact the lower Chester at all. And they were similar for both of these models. It's also interesting, I think, that to look, there's an interesting pattern in terms of chlorophyll, where the TSS is very high now, chlorophyll actually drops. So the water is cloudy, less production, chlorophyll goes down, so there's nutrients that aren't used up, that those nutrients are transported farther downstream, so you have more growth down here and actually get increased chlorophyll downstream. So that effect is showing up in both models. So that's what happens if we change the rivers. So now what happens if we change the bay? So the differences are a little smaller, especially for suspended solids. But the interesting thing here is that you feel the river feels these changes from the bay, open bay, roughly about 40 kilometers upriver, which was really quite surprising to us. So and we see that distance is similar for the both models. So they're very sensitive to what's happening in the open bay. So just to summarize for this part of the talk, basically I think one of the take-home messages is that water quality in these shallow regions is really difficult to simulate. We see large differences between the model results, the actual concentrations, even in the high-resolution models, between the chlorophyll and the suspended solids. The high-resolution models actually reproduce the data quite well in terms of DO, but the low-resolution model for DO is way too low in the upper and lower Chester. And one of the things that I didn't have time to talk about too much is that we really feel like it's Schism's high-resolution bathymetry, which is impacting residence time, and is probably the reason why it's leading to an improved chlorophyll simulation. Also, we found that the high-resolution models actually are producing very similar scenario results, even though the models themselves produce very different DO concentrations and chlorophyll and suspended solid concentrations. The improvement due to nutrient reductions is very similar between the models. And that's really heartening. That's good news, because that's what is used for the TMDL decisions, and that's the way these models are used. They're used by looking at the percent improved, the actual improvement. And in that respect, the high-resolution models perform very similarly. But we do see that the low-resolution model produces very different scenario results, in fact, by, for example, still showing hypoxia under the all-fours scenario, while the high-resolution models actually show little hypoxia even under the TMDL. So I know that was a lot a lot of conclusions there, but we really wanted to just kind of finish up here by giving some recommendations to the Bay program and going forward in terms of what a next generation model of the shallows might look like. So we came up with about 4 points here. Essentially, we really feel like we need this high-resolution model that can resolve the bathymetry well and the coastline well. It has enough vertical resolution really to resolve that estuarine circulation all the way up into the upper tributaries. And there's another advantage here too, is that if we have this high-resolution model, we can really include the local processes that can form management on these scales. We also really need to use multiple, at least, research models, even though we may have only one management model for ultimate decision. Having these multiple research models in the community is really helpful. It allows us to examine alternate formulations. It has allowed us to find errors and inconsistencies in our modeling and our methods, and really we can learn from each other. I think everyone participating in this project really did learn from one another. And finally, it also increases confidence in the final results. If the models all produce the same result, it gives us improved confidence. Another highlight that really came out of this work that I mentioned was that it really seems very important to have online or two-way coupling between the hydrodynamic and the water quality models to make sure the water quality, the ecologically relevant variables are really responding to the best hydrodynamics that we have. And finally, another really clear point that came out of here is that we really need to carefully consider this connection between where the tributary meets the open bay. We don't really recommend separate models for the shallows and the main stem. What we really need is a seamless transition, either via nesting or some type of hybrid grid to connect the shallows with the open bay. So these are some of the main overall take-home messages from the project, and we really hope they're going to be useful for the Bay program as they move forward, thinking about what the next generation estuarine model is going to look like. I'll end there.
so much, Margie. We have time for a couple of questions. Yes, we have that hand first here.
You said that the predictions are very sensitive to bathymetry. And so how accurate is your measured bathymetry?
I feel like it's that's just not the limiting factor. Here I think we used a 30-meter digital elevation map. I think there's even better out there, but the grids are less. So I feel like that's not anyway. Other folks can pipe up, but I feel like that's not the limiting factor. It's actually interpolating that onto the higher resolution grid. That's the issue.
Can I follow up?
Yeah.
Can I follow up with a quick question?
Sure.
So then you also said the DO for the regulatory model, the bottom DO wasn't well predicted. So is that just because it doesn't predict stratification well?
That's part of it. I think that there are other issues as well going on as well, and we haven't. But I think that's one of the take-home messages. I think we can't get it right if we don't get the stratification right. I think if we got the stratification perfect, we might still have issues, but that I think is the first thing we need to deal with.
Other questions? Yes, Bill.
So Marty, very nice talk, a lot of information there. My comment and question have to do with all the models and the observations. And I noticed early on in one of your slides that the base salinity changes in the observations now lag behind freshwater runoff by several weeks, 3 weeks and sometimes. And something perhaps related to that, all of the models had the most trouble seeing salinity around the middle of the river, around the 30-kilometer to 40-kilometer range. And what I'm wondering is how the models deal with groundwater. Can you explain whether they include groundwater and any influence of that at all?
No, I'm quite sure that none of the models include groundwater. So that is. I think, and we have looked, and I didn't have time to put it into this talk, but at the relative timing of events, how quickly the models can respond to the timing. That is an issue, responding quick enough to when you have a big event. So that's getting that lag right, or having a steady lag is something that the models are maybe working on too.
Do you have a sense of can we look at groundwater?
Possibly. I think we have a couple different storm events. We've got Hurricane Isabel coming in. So with Hurricane Isabel, groundwater is just a tiny little fraction of that huge signal coming in from the bay, and the whole the whole river gets all salty. And then we've got this storm of a century in 2006 that came in and flooded the Washington D.C. and so we have these huge events. So compared to those huge events, the groundwater is pretty minor. But of course, in more standard times, when you don't have these huge events, groundwater would be quite important.
Don.
Yeah, the heroic effort. The difference among the models in terms of the water quality parameters were striking. And even though it led me to think that there are some meaningful differences in the biology and chemistry that are greater than the differences in spatial resolution and hydrodynamics. Is that true?
I think so.
Is there some learning that can take place?
I think so. I think this was all done without as much resources as we would have liked. So I think given more time, given more effort, I feel like the modelers would have actually tuned their models even more to the data that we have available, and then we would have seen the differences converge. But it was actually kind of interesting. We didn't give them much time. They gave us what they had. But I think it's really challenging. I mean, keep in mind, the three models were all using the same model. I mean, they may have little tweaks, difference in the way they were implementing, but I think those my feeling is absolutely, like you say, that's due to these minor differences between the different model implementations, not due to the grids. So, yeah.
Okay, we'll take one more quick question here.
Yeah, all of the simulations seem to show a peak at 10 meters. Do you have any explanation?
So that was I showed a lot of bottom concentrations, and that was one of the deepest points in the bathymetry, right in that deep curve before the Chester River comes around. That's one of the deepest
In terms
places.
of depth or?
In terms of depth.
Curvature?
Both.
Thank you.
Okay, and I think we'll cut the questions off. You can talk to Margie during break. We're going to go to break. So let's thank Margie again.